Hello, everyone, and welcome to another session of our literature survey season. Today's focus will be on ML for finance. If you missed the previous literature review sessions and want to catch up, then you can find it on our YouTube channel. So, today I'm pleased to introduce you to Prasad Seemakurthi, who has joined all the way from Bangalore, India. I guess I'm supposed to pronounce it as Bengaluru. Who will present a literature survey on applying deep learning methods for financial applications. Prasad is a data science manager at Nami FinTech and has previously worked in the United States and Singapore. So, over to Prasad.
Thanks, Suhas. Thanks for the introduction. Today, we'll be discussing about a survey of deep learning in finance world. The authors of the paper are Ahmed, Mehet, and Umar. I hope I got their names correct. So the agenda for the session is going to be like, we will be discussing about what areas or where people have used deep learning in financial world, and along with what are some of the interesting problems that people have solved. Um, and even though it's a survey, I wanted to do a deep dive of at least one paper. I will be looking into a deep dive of a fraud use cases in credit card industry, where I've been working on a similar problem for the past 4.5 to 5 years. Along with the survey, we will see that what are the areas that has a promising potentiality of deep learning applications and the future direction of deep learning in finance, and some of the stats basis the papers that the authors have surveyed. So before we dive deeper into the survey, a quick recap of what some of the architectures of deep learning. The first architecture that we're going to see is fully feed-forward, fully connected neural network, where the input, where we do have a multiple layers, where the input is where we do have an input layer followed by a bunch of hidden layers, where each hidden layers will have a bunch of nodes connected by the weights and activation functions along with the biases. The feedback will be propagated throughout the network using back propagation. The second architecture is convolution neural networks, typically used for classifications of image. We have an input layer followed by the convolution layer and followed by the pooling layer used for reducing the network size, etc. The next architecture is RNN, recurrent neural networks. Whenever we have a sequence data or a time series data, we want to RNNs are typically used. Due to the limitations of RNNs like exploding and vanishing gradients, people have come up with a new architecture called as LSTMs, where both the problems has been addressed to a large extent. Now let's look at the different use cases and fraud detection space. So before we delve deeper into the use cases, we want to understand why to solve the problems. So a survey from BCG says that there was a fraud in tunes of more than $3 billion just in the US for the year 2017. So it's a very, very researched and well applied area in the finance world. Some of the use cases are credit card fraud, anti-money laundering, tax insurance, and these are some of the areas where mostly people have tried solving with soft computing, typical expert systems, then traditional machine learning, and then they eventually moved from ML to the deep learning world. So most of the problem in the fraud detection area would either fall into a classification or an anomaly detection areas. The most commonly used deep learning deep learning architectures in fraud detection are feed-forward neural networks and LSTMs due to the underlying nature of time series data. Deep autoencoders has been more of a research area in fraud detection in order to detect the anomaly in the use case like anti-money laundering. Basis the survey of the papers, a couple of novel ideas in fraud detection is applying of deep Q learning, which is a variant of reinforcement learning to predict the risk averse from firms' tax evasion and other behaviors. As it is a very well applied area in the industry, there have been a lot of papers on it. Some of the interesting papers or the use cases are These are some of the interesting use cases. Uh, so what this slide typically represents is what is the data set that the people have used and when was the paper has been published and what features that the people have used and the method, evaluation metrics, and the performance criteria. So if you look at the fourth use case, credit card transaction, people have taken the data from 2015. The feature set contains the transactions and the bank features. LSTM has been used as an architecture for training the model, and area under the curve has been used as an evaluation metric, and the tools like Keras, Scikit-learn have been used to train the model. There have been some of the use cases on the real world data sets as well. For example, uh, uh, there is an author that has actually applied deep learning on the real world data for the automobile insurance. So the feature set for that is insurance claims related to the car and the accident related features. The method has been used deep neural networks along with latent distributed allocation. True positive and accuracy, precision, and F1 score are some of the metrics used as a performance criteria. Let's look into a deep dive use case of how people typically apply deep learning in the financial world. So we are going to discuss about a paper authored by Abhimanyu Roy and all. The title of the paper is Deep Learning Detection Fraud in Credit Card Transactions. So as I said in a couple of few months ago, and deep fraud is a very important problem to be solved in financial world. So the architecture, what the author have done is like they have compared four different deep learning architectures, and they've trained it on a real world data set provided by the Capital One. The data set contains 80 million anonymized transactions over a period of 8 months from Capital One. So some of the attributes includes transaction amount, merchant information, like where the transaction has happened and the time of the transaction, etc. And also the account age. What it means is how long the customer the person been a customer of Capital One Bank. So the output variable is going to be either a transaction would be classified as a fraud or a non-fraud. Like most of the use cases in fraud, the data is highly skewed. And in the current data set, the class imbalance ratio is in the ratio of 99.86 is to 0.14. It's a highly skewed data set. If we delve deeper into the implementation details, data pre-processing, they tried handling the missing values. The data contains a lot of missing values. For all the continuous variables, they have used mean as a mechanism to impute the missing values and mode for the categorical variables. Along with, they have created a bunch of columns which indicates whether a value is missing for a particular feature or not. They have actually trained the models with a tenfold cross validation across all the architectures. So deep learnings are one of the successful attributions to deep learning is like automatic feature engineering, which seems to be pretty successful in unstructured data. So the authors have tried comparing the models on the data sets that have received from the bank directly itself. On top of it, they have also created domain-specific features like frequency of the transactions that the user has done in the last 1 month at a user level or at the account level. For example, if a person is holding more than one account, they have considered each account as a different time series in the model. So other variables like account history, the number of transactions, the time where the user has done the transaction, etc. So in order to handle the class imbalance, what they've done is like they've undersampled the majority of a majority class at an account level rather than at a random sample transactions. There's a reason why the authors have done that. The underlying data has some sort of a temporal relationship, due to which what they've done is like they have sampled accounts and included all the transactions belong to that account as a part of the model. And they've also tried with different ratios of majority and minority class. And it seems like the ratio of 10:1 yielded the best results among different architectures. So each architecture is a fully connected neural network that contains 6 layers with a backpropagation algorithm. So there are some of the interesting findings from the experiment. So some of the hyperparameters they try to tune are the depth of the network, learning rate and dropout rate, activation and loss function are some of the hyperparameters that tried optimizing in order to achieve a better error metrics. One of the interesting finding from the paper is that the impact of learning rates are pretty inconsistent. There is no straight or linear relationship between the learning rate and the error metrics. It's quite chaotic. Apart from the learning rate, other hyperparameters are not really impacting the outcome. They have also presented the sensitivity analysis of all the architectures. For example, if you look at the first slide, if you look at first slide, we do have four different deep learning MLP models that has been trained with different hidden layers. The first one here, we can see that the model has been trained with three hidden layers, four hidden layers, five hidden layers, and the six hidden layers. As and when we keep increasing the depth of the network, there is the error has been optimized accordingly. Similarly, in LSTMs, the people have tried with 3, 4, 5, and 6. Here also the trend seems to be pretty consistent. Uh, the results of the experiment that the people have done. This is the table that represents the results. Before we delve deeper into look into the results, let's look at the architecture of all the four. The hyperparameters of all four different architectures. Each architecture has had 6 hidden layers and 150 nodes per each hidden layer. They have used LBFGS solver for deep MLP, and TANH as an activation function across the remaining architectures. They've tried playing with different learning rates as well. For ANN, the better learning rate turned out to be 0.05. For ANN and GRU, gated recurrent units at 0.05. For the rest of the deep learning algorithms at 0.5, and they've used mean absolute error as an error function to evaluate the final outcomes. ANN seems to be the worst performing model among the given four different models, and GRU has a better output compared to the rest of the models. The next area where people have used deep learning predominantly is risk assessment. Let's look at the definition of a risk assessment. Risk assessment defined as an assessment measure of risk of an asset, firm, product, person, etc. So examples in risk assessment are credit scoring, bankruptcy prediction, loan or insurance underwriting, etc. So majority of the applications in retail banking, like credit scoring and distress classification, risk transaction detection, are being used where deep learning has been heavily used. Credit scoring has been pretty important area for retail banking. If it is not handled properly, it leads to huge write-offs and losses. Deep learning has also been applied for identification of banks distress by extracting the financial signals from the financial news. So there are a couple of novel ideas in risk assessment segment as well. Class imbalance has been a major challenge in risk assessment because uh, very few organizations or the firms will go bankrupt. So to handle the class imbalance, what people have done is like they have created a multiple subspaces of the majority classes, and they've added all the minority classes to each subspace before feeding it to the classifier. Any questions? All right, let's look at some of the applications of credit scoring, deep learning applications in credit scoring. People have applied credit scoring across different data sets like German and Japanese banks data sets. The feature set contains variables like personal information, like the name of the age of the customer, the educational qualification of the customer, the financial worthiness of the customer, so on and so forth. So the commonly used deep learning methods across credit scoring or classification is deep belief nets, RBMs, autoencoders, and deep neural networks. Some of the commonly used evaluation criteria are area under the curve, false positive rate, false negative rate, accuracy. etc. People have used mostly Python and scikit-learn and Keras as a tools for building the models. If you look at the tool, if you compare the tools with academia, right, most of the people in this space are practitioners. They're more worried about deploying of the model into production. That's the reason behind selecting these tools for developing the models. Yeah. Sorry. Let's scroll next. Hmm. So the next area for deep learning is algorithmic trading. So there are variety of use cases where people have applied deep learning in algorithmic trading, so, varying from simple use cases like what stock to buy, what stock to sell, what prediction of the open, close, high, low values of a particular stock or an index, ranging to the sophisticated use cases like bid price, ask price, spread, etc. Uh, so most of the papers have used LSTM as a technique to develop the model. Again, due to the reason that the underlying data follows time series patterns, and a lot of real world use cases has been people have used LSTM. For example, people try to predict the index value of S&P portfolios of cryptocurrencies, etc. Uh, and this is an interesting area. A lot of people are experimenting by combining both CNNs and RNNs, which is an interesting area to watch out. And the novel ideas in this space is use of deep reinforcement learning and pre-processing of the financial data. I mean, they converted the structured financial information as a part of the image and fed to this maintenance. It's a very interesting approach. Again, there have been again a lot of real world use cases. If you look at some of the use cases, like people have tried extracting the financial news from Reuters and Bloomberg, and they've created the Dr. Wax, which is as a pre-processing layer before feeding it to the deep neural network. In terms of performance metrics, again, nothing different. Couple of people have tried using other things like negative average log likelihood, accuracy, and RSC, like the other things. The tool set has been evolved when we compare to the other applications because the data sets are really large or huge to process. That's the reason why people have tried using more of an sophisticated libraries like TensorFlow, Keras, PyTorch, etc. So yeah. So, the next area in terms of application of deep learning is portfolio management. The definition of portfolio management is the process of choosing various assets within a portfolio for a predetermined period in order to make profits. Under the hood, portfolio management is nothing but an optimization problem involving which involves like identification of best performance of assets like stocks, bonds, so on and so forth. Typically, people have used deep learning in order to predict the T plus one value. It could be the index value or a stock value, etc., where T could be a time period like a day, week, or a month. RNN seems to be RNN and its variants like LSTM and GRE seems to be the primary model people have used in order to construct the portfolios. The novel idea in this space is again DRL is being used for portfolio allocation and the application of deep learning in the price forecasting of cryptocurrencies. Even though the availability of the data in the cryptocurrencies is limited, still people are trying to use deep learning to forecast on a sparse or less data as well. Um, so these are again some of the examples of application of deep learning in portfolio management. We can see that there are a lot of real world use cases. People have used a data set containing the bitcoins like Ripple, Litecoin, etc. And if you look at the periods in which the model has been trained on, people have taken the data from all the way from 1987 and they try to mix it with the recent data and tried making the models, which is a very interesting phenomenon. When we look at the different methods that are used, the complexity of the algorithms has been reasonably good, relatively good when we compare to the other use cases. There are a couple of reasons why people have done that, because explainability, when we use a black box model, something like a deep learning, explainability would be difficult to draw the inference. These are the areas where people, these are the applications where it is not really audited or regulated much. So people worry about the accuracy or the precision of the precision rather than explainability. That actually opened up a new avenues to use much more sophisticated models like reinforcement learning, etc. um, Again, in terms of the toolings, people have used distributed computing things like Spark, TensorFlow, and off the book or off the shelf models from third-party vendors like H2O, etc. Um, the other area of application of deep learning is financial sentiment analysis and text mining. One of the with the recent improvements in text mining has led to the successful extraction of sentiment from the unstructured data. So with the availability of, with the proliferation of social networks, right, people the investors' mood has been one of the major signal for which is one of, turned out to be a major signal which predicts the fluctuation in the stock market. For example, if you look at some of the stalwarts in investment industry like Warren Buffett or Elon Musk, a recent example where Elon had actually tweeted that the stock price of Tesla seems to be really high in his opinion. The one tweet has actually wiped out $14 billion of Tesla stock from the market. So with the improvement or the maturity of the tools, right, people want to consume different sources of information across Twitter and other financial feeds in order to improve their models and make their models more sensitive to the recent availability of the data. Typically, people take the unstructured data, they convert into word embeddings using some of the deep learning techniques like word-to-vec, etc., and they feed to the final deep learning architectures like LSTMs, HLMs, CNNs, etc., for the final prediction. This area, again, a lot of innovation is happening. People are trying to come up with hybrid architectures. For example, word embeddings are created out of using word-to-vec as a feature engineering step, and the output is fed to recurrent convolution neural networks for the final stock prediction. Again, these are some of the real-world use cases of text mining using deep learning. So people have tried to forecast the stock price by combining the data from news, Bloomberg, social networking, various other things. And if you look at the methods that they've used, again, fairly sophisticated compared to the first initial couple of use cases. Again, when we look at the toolings, again, people have tried using distributed computing toolings like Spark, TensorFlow, Scikit-learn, etc. Some of the statistics, this is the papers that the authors have surveyed. In total, 144 papers across different financial applications has been reviewed. Some of the journals includes IEEE, KDD, and various other applications along with the use cases from the real world industry. It's an interesting phenomenon to see that most of the papers has been published in the last 3 years. If you look at the ratio of the papers that have been published in the last decade compared to the 3 years, the ratio is pretty close to one. And financial text mining seems to be the area where there are a lot of people who are applying deep learning. As I mentioned previously, it is because the industry is not really regulated and people really not care about the explainability of the models rather than they worry about improving the precisions and various matrices. If you look at the histogram of counts of publication per year, so before 2012, people have not used much of deep learning. Occasionally, there are a few people who have tried applying deep learning in the financial world, and it has been primarily from a research standpoint rather than a industrial application standpoint. So let's look at some of the models that have been used. RNN seems to be the most prominently used models, even a decade and even in the recent times as well. CNN seems to be catching up the play. And when we look at the different tools, the toolings that are used to build the model, Python and Scikit-learn seems to be most prominently used tools. The reason, I mean, these trends may not be in lieu with the recent trends because the authors have surveyed the papers all the way from 1988 till 2020 February. So TensorFlow and PyTorch has been developed in the recent part. That's the reason why a lot of papers have mentioned other things like Tano, Keras, Spark, etc. Uh, and if you look at the preferred development environment, Python seems to be the most preferred environment in terms of developing the applications. And there are other more lesser known frameworks like Java and Tableau, etc. They've used it as well. When we look at the preferred libraries, Keras, Python, PyTorch seems to be the prominent libraries for developing deep learning models. Future direction. So now that we have actually looked at what people have done in the past, let's look at what the authors believe that deep learning has it in the future. Deep learning seems to be more of a hotter area in relatively unregulated application areas like high frequency trading, cryptocurrencies, blockchain, etc. Behavioral finance, which typically been a major driver in the common investment area, is fairly untouched because of the data being unstructured and difficult. It's really difficult to actually parse a lot of data sets, and this seems to be having a lot of interesting potential in the near future. Summary, if you look at the total summary of the paper, deep learning models prove to be better or at least as effective as traditional machine learning models. Deep multi-layer perceptron and RNN seems to be the most predominantly used models among the financial world. With more than 70% of the paper are citing LSTM, it is the most commonly used variant of RNN in the industry. CNN started to gain the momentum in the recent years. Uh, there are a couple of there are a bunch of innovations that are going on in CNN. As CNNs are primarily used for image classification, people are innovating to represent the data, structured data as a 2D image, which they can actually feed it to the CNN convolution neural nets and make a classification output. So there are again much white hot research areas in finance, like people are using graph CNNs and deep reinforcement learning in order to solve some of the complex or complicated problems like anti-money laundering, etc. Algorithmic trading, portfolio management, and risk assessment continue to be the dominant areas where deep learning has a lot of use cases. That's the summary about the paper. Any questions?
Hey, thanks for the presentation, Prasad. And
Yeah.
we have a comment from Willie. Um,
Mm-hmm.
he says, for portfolio management specifically,
Right.
state of
Mm-hmm.
the art may not be published because the success
Right.
is based on information advantage.
Correct.
Uh, so, what do you have to say about that?
So not only in portfolio management, so I mean, the better the data that we feed to the model,
Mhm.
the better the output is going to be. And yes, portfolio management is one area where people don't actually publish state of the art.
Mhm.
But what the authors have done is like they have taken all the papers that has been published in the open world. That's the all the opinions and the matrices has based on the papers, the information that is available in the public domain, rather than reaching out to the industry veterans.
Mhm. Okay. We have a question from Robert, who
Mhm.
says, could you please elaborate on the format of data that is typically used in these applications? So something like what are the feature vectors, the structure, and if any typical feature extraction is applied, especially for time series.
Yeah, I mean, if you look at, let me go through the initial slides where we do have some of the features. For example, credit card transactions. I mean, if you look at for example, let's say a person has been transacting with a bank over a period of 1 year, and
Mhm.
his card has been stolen. The underlying data follows a time series pattern, and the way how people typically use such kind of time series is like they create a string of transactions as an input vector, and they feed to the models like LSTMs and GRUs. That's how typically people does it. For example, I have while I was actually at a company called American Express, I have built a string of repayments in order to identify uh, whether a given customer will be making the payment in the next month or not against his outstanding balance.
Mhm.
Yeah.
Um, Robert, does that uh, answer your question? I hope it does. So, another question from Robert is asking, so the delta time between 2 points isn't constant, right?
Correct. So we'll have to sample it and make it constant. For example, not all transaction will happen at a constant space. So a couple of things what we can do is like we can aggregate the transaction to a certain time frame. For example, I'll create a node at every end of every day at a given time. I'll sum up all the transaction amount and create a string with let's say to be very specific or concrete. For example, I wanted to predict whether the guy will default basis his card transactions. Like Robert rightly said, not all transactions will happen at a regular or evenly spaced time intervals. What I do is if I've decided to actually take 6 months worth of data to build my final model, I can say that I will sum up all the transactions at a weekly level, and I create an equal string for all the customers where uh, each vector would represent the 6 months worth of data. If there are if there are any persons that doesn't have 6 months worth of data, what we typically do is like we can pad it using a constant number, which is not a part of the data set, and we train the model.
Hmm. Okay. Um, so, as I heard that you have worked all across the globe. So I worked in the
Mhm.
United States, in India, and
Not really
Singapore.
across the globe. Yeah, India, Singapore,
But
and
yeah,
yeah,
yeah, and have an experience of 5 years in the financial space for data science. I was just
right.
curious, how receptive are the big legacy players in other parts of the world when it comes to adopting machine learning techniques or even
Mhm.
deep learning techniques. And
Right. So I can't actually speak for across different industries in the finance. My experience has been largely related to the retail banking side. I
Mhm,
worked at companies like American Express and some of the trading organizations. So machine learning as a field has been, I mean, like banks have been using machine learning as a field since long time. They call it with a different name called as a risk management. But I mean, there was a lot of resistance when people wanted to move from ML to DL, in
mhm,
especially big companies, big companies. The reason is there are a couple of reasons, to be honest. One, if something is a black box, people are not really confident in productionizing that. what they wanted to make sure is there is a minimum disruption when they deploy something into the production. So that's a big reason why people are really not willing to move from ML to DL. So I happen to transition at least three use cases from a regular deep machine learning based models to a deep learning based models, and the transition happened in phase wise. So what I did was, rather than using deep learning as a final model, we used deep learning as a tool to create additional features that would go as a part of the more of a traditional machine learning, like boosted trees, random forests, or something like that. So once people have trusted the outcomes of these newly created features, people have figured it out that deep learning can be a good use case in building the final models. At the same time, there are a lot of frameworks that are being developed to draw the explainability from the black box models like deep learning. Not so another reason is that finance been more I mean, at least the retail banking has been a very highly regulated or audited industry. So you can't I mean, if people follow the financial news, recently Goldman Sachs and Apple has been backlashed because the models that these people have developed are biased towards Yale. Uh, that actually lead to a lot of uproar in the industry. So due to which auditors have become extra cautious and they wanted to understand why a particular decision has been made. So there are challenges, and overall the industry is actually moving towards adopting deep learning for solving some of the difficult use cases.
Mhm. So Amir has a question. So
Mhm.
you have uh, showcased several dozen kind of use cases in the financial
Mhm.
industry where
Mhm.
deep learning has been used. Um, so how many of these are like just still proof of concepts, and how many of them are regularly used in production? Is there what are like
Yeah.
the commonly, yeah,
Um,
used?
So to be honest, I mean, it's nowhere mentioned in the paper, to be honest. I mean, basis my experience, I can say that in retail banking, people are still catching up using deep learning. So for more of a, I mean, people may not be using deep learning for more of a traditional use cases like fraud detection, basis the transaction and all. I mean, people may not be using in the applications where auditors are auditing the applications, but people are embracing deep learning in less audit space, like should I increase the line or decrease the line on a credit card. This is the behavior of the user, right? So nobody will be questioned why did you actually reduce somebody else's line from the audit standpoint. What they would be more interested in is like if a transaction is being declined, they wanted to see like why a particular transaction has been declined, or if a credit application is declined, they wanted to understand the reason behind declining of a credit application, rather than they'll not be worried about like what should be the size of the loan to be given, etc. So to summarize, in the areas where audit doesn't happen much, people are embracing deep learning, versus in the areas where audit happen a lot.
Mhm. Um, yeah, thanks for the answer. Um, okay, so maybe not as much related to finance, but are you wearing
Mhm.
a Manchester United shirt?
Yeah, yeah.
Uh-huh. Interesting. So, uh, if there are no more questions, I think we'll be
Mhm.
ready to wrap it up. Thanks, Prasad, for the talk. And to our audience, just a note, in just over an hour from now at 12 p.m. Toronto time, we will have Felipe Petrovsky Such from Uber AI talking about generative teaching networks. If you are interested in meta learning, neural architecture search, etc., come join us. It's going to be fun.
Yeah,
Um,
thanks. Sorry, go ahead.
yeah, sure.
Yeah, I really want to thank ACE for providing me an opportunity to give this talk. Um, the host has been super nice. They've been following up for the past 1 week to see like what all the things required from my end to make this talk successful. I want to thank you guys from the bottom of my heart.
Okay, thank you. And I am looking forward to see a lot more applications in the world of finance that
Mhm.
use advances
So,
in machine learning. Yeah.
right. So there are a couple of interesting use cases which are not a part of this paper, which I'm currently working on. If people are interested, I can talk about those. Maybe couple per minute. For example, I mean, most of the world has been moving from a brick and mortar kind of a banking space to more of a digital banking, and these transitions happening in more of a developing and underdeveloped economies where the population is really huge. So when anybody wanted to open up their account, one of the key pieces is something called as know your customers, KYC due diligence. So banks wanted to make sure that they're not dealing with people who has been sanctioned, etc. So deep learning has been a major enabler in this area. For example, if I want to open up my, let's say, set up my bank account in countries like Singapore and India, rather than me visiting the branch, what I would typically do is like I'll log into one of the banking applications and I'll upload my verification document, something like my passport or a driver's license, etc. Deep learning, people are extensively using deep learning in these areas to identify whether the uploaded document is been a tampered document or not. So deep learning has been, I mean, with the help of deep learning, it's been an enabler in order to uh, reach masses. Imagine that I need to, I mean, let's say I'm a bank that I want to start up and I'm targeting to onboard 1 million customers within a span of 1 year. If I have to physically process each and every account, I would easily end up spending like a billions of dollars just to onboard the customers. Versus I can build a I can take a state of the art deep learning model and reduce the cost by hundreds. To answer Amir's question, there are a lot of use cases where people are using deep learning in the financial world, but these are use cases are not mentioned as a part of the paper. That's why I have not mentioned earlier. Yeah. On that note, I'm done with it.
Okay. Yeah. Thanks a lot. And yes. See you at 12.
Yeah. Thanks, guys.